This transmission line is feeding 60,000 kilowatts of power into the system of the Duquesne Light Company, serving Pittsburgh, the steel city of the United States. The origin of this power is this atomic power station on the Ohio River at Shippingport, Pennsylvania. Primary objective: to gain information and to advance reactor technology. In addition, the objective was to obtain a nuclear power plant that would be readily operable in a conventional electric utility network and with a high availability at all times. It is the first full-scale nuclear power plant for generation of electricity in the United States. Westinghouse Electric Corporation developed and designed the atomic reactor under the direction of and in technical cooperation with the Naval Reactors Branch of the United States Atomic Energy Commission. Duquesne Light Company provided the turbine generator and is operating the entire plant. Hundreds of other companies, large and small, made valuable contributions to the project. The plant's generator was synchronized with the utility system just 16 days after the reactor went critical for the first time, and 5 days later, 60,000 kilowatts, the reactor design rating, went into the transmission lines. Now, what made this achievement possible? This film report will show, in part, what had to be done from proposal of the project to production of the power. Basically, the pressurized water reactor station operates on a simple principle, embodying a primary and a secondary heat transfer system. In the primary system, ordinary water of high purity, kept under pressure to prevent boiling, is pumped through the reactor. This contains uranium fuel and control rods. The water serves as a neutron moderator as well as a heat transfer medium. Heated by the fuel, the water flows through a heat exchanger. There it gives up some of its heat, is then recirculated by the pump, repeating the cycle. In the secondary system, which comprises a separate water circulation system, saturated steam is generated in the heat exchanger, flows through a steam drum containing steam separators, and through a turbine which drives the generator, then goes through a condenser, and as water is pumped back to complete and repeat the cycle. The use of separate systems prevents the possibility of transferring radioactivity from the primary system to the turbine and condenser. Specifications were drawn up by the Atomic Energy Commission in 1953 and included generation of at least 60,000 kW net electrical output from saturated steam at 600 pounds per square inch, ordinary water as the coolant and moderator at 2,000 pounds per square inch pressure, and fuel element life as long as possible between chemical reprocessings, with an initial goal in excess of 3,000 megawatt days per ton. There were several other stipulations, with safety within the plant and its vicinity to be an overriding feature. Here then was the basis on which the plant was to be built, a plant that would provide experience and experimentation for the benefit of future nuclear power stations, a facility in which a variety of reactor cores may eventually be operated, a plant made possible by a close working relationship between government and industry. These basic ideas evolved into this schematic plan of the Shippingport station. It makes use of 4 similar loops, all supplying steam to the one turbine. Any loop can be shut down for maintenance or for instrumentation to permit studies and experiments while the plant is operating at full capacity. Behind the successful completion of Shippingport was the blazing of trails into new territory. The solution of countless problems in physics, chemistry, engineering, manufacturing, and construction. These problems, many completely without precedent, fell into four general areas, the first and foremost being the reactor. It posed many new, complex, and interrelated problems in design and in technology. They involved determining the most suitable fuel materials, designing the sizes and configurations of fuel elements, processing of fuel materials and manufacturing elements, determination of control rod material and design, detection and location of any failed fuel elements, the complex instrumentation needed for the gathering of highly useful information on core and plant operation, and the design of the reactor vessel. In the second area were problems involving the water. What operating temperatures in the primary system? How to control a 2,000-pound pressure? How to minimize corrosion? What measure for water purity? The third area concerned problems of assuring complete safety for persons in the plant and in the surrounding area. These problems involved shielding and measures for containment of fission products. The first barrier confining the fuel, a second one confining the primary water, and a third barrier, the plant container, surrounding the entire nuclear portion of the plant. In the fourth area were the problems of special equipment, zero leakage pumps of unprecedented size, large remotely controlled hermetically sealed valves, instruments to continuously monitor reactivity from source to above full power levels, and operational radiation monitoring equipment. The solutions to some of the shipping port problems are evident in the physical form taken by the plant, as seen in this scale model, 1/40th the size of the actual plant. The thick walls of ordinary reinforced concrete provide effective neutron and gamma shielding. Their thickness averages 5 feet. At the heart of the plant is the reactor, inside a 38-foot sphere, topped by a dome 18 feet in diameter. The pressure vessel is over 10 feet in diameter and 33 feet high. Within it, of course, is the fuel and the control rods. 3 underground chambers, steel shells 50 feet in diameter and 1.25 inches thick, along with the sphere containing the reactor, make up the plant container. This is one of the 2 similar boiler chambers. A concrete shield separates the 2 loops within it, permitting access to an inactive loop while the plant is operating. The steam generator consists of this steam separator and heat exchanger. The 4 loops are capable of producing a total of over 1 million pounds of steam per hour. This chamber, 150 feet long, is used for auxiliary equipment such as the primary water pressurizer and the pressure relief system. This is the canal area for underwater handling of irradiated fuel, with facilities for core disassembly and temporary storage of used fuel. Before the plant could become a reality, most of the problems of materials, sizes, shapes, and workable arrangements had to be solved. The biggest and most important problems, naturally, were those concerning the reactor. These were solved at the United States Atomic Energy Commission's Bettis plant. There were many problems in physics to be solved. The first of these was to establish a core pattern. This required reactor physics analysis and thermal and hydraulic calculations. Mechanical design studies and investigations of fuel element configurations and materials were also being made. One of the aspects considered was the desirability of using two types of uranium instead of the single type of slightly enriched uranium that was originally contemplated. If some highly enriched uranium could be used along with the much larger quantity of unenriched or natural uranium, there might be many advantages, economic as well as physical. In this new concept, the enriched material was referred to as seed, and surrounding it would be a blanket activated by the seed. The pattern evolved was that of a hollow square of 32 seed assemblies with blanket assemblies both inside and out. But such a blanket would have to satisfy certain requirements. The material must pass severe tests of corrosion resistance to high temperature water. Radiation stability was necessary so that cladding would not tend to rupture. If elements failed, the failure should not progress to other elements, and the blanket fuel must contain maximum uranium loading or content. The problem was that no such fuel materials were known. It was necessary to establish an extensive metallurgical program to do research and develop technologies. It was recognized, first of all, that metallic uranium could not serve as blanket material. It had very poor corrosion resistance, for one thing. Perhaps, however, a uranium alloy could be used. Molybdenum, niobium, and silicon were among the possibilities that were investigated at Bettis. Another material being studied was uranium dioxide, UO2. Though little known, it merited study. It was corrosion resistant because, as an oxide, it was in effect already corroded. Furthermore, tests indicated good irradiation stability, and it met the other criteria. But its physical properties were not known. Even such fundamental properties as melting points and thermal conductivity had to be determined. Many aspects of the chemical behavior of the oxide were studied. These included such things as its reaction with hot water, its reaction with a zirconium alloy, which might be used as cladding, and the effects of particle sizes on chemical behavior. It was found that UO2 could be sintered successfully if carried out in a hydrogen atmosphere. This process increased both density and strength. Many tests, including in-pile irradiation, were performed on uranium alloys and UO2. Included were tests on intentionally defective samples. Based on these tests, the oxide offered the most promise. Accordingly, it was selected as the blanket fuel. Although the development of the manufacturing processes was then begun, the extensive test program was continued to verify the selection of UO2. More than 2 million uranium oxide pellets and 95,000 blanket tubes were made. Processing of pellets included agglomerating, compacting, sintering, and grinding. Fuel rods and bundles were assembled, argon atmosphere welded, annealed, and machined. In the meantime, seed elements were also being made. The basic component of the seed cluster is an enriched uranium fuel plate. It is sandwiched between two zirconium alloy cover plates. Sub-assemblies were joined with the necessary spacers to create a cruciform channel for the control rod made of hafnium. Hafnium, being a good neutron absorber and having high corrosion resistance, is ideally suitable control rod material. While fuel manufacturing proceeded, extensive reactor physics calculations were performed to determine the design reactivity of the core. A certain amount of excess reactivity, to be controlled by the control rods, had to be provided to compensate for fuel depletion, for the buildup of fission product poisons, and for reactivity changes between room temperature and operating temperature. To provide for experimental checks of the calculations, a flexible critical experiment, in reality a nuclear model of the core, was constructed at the Bettis plant. It was designed to operate at room temperature. Using this critical assembly, calculations of reactivity at room temperature could be checked with reasonable precision. But the reactivity at operating temperature could be anticipated only on the basis of calculations. Initially, there must be sufficient reactivity to sustain criticality or a neutron multiplication constant of 1 or unity. The excess reactivity was designed to include 6% for fuel depletion, 4% for fission product poisons, 3% for temperature changes, and 5% for design margin to allow for the uncertainties in the design of this unprecedented type of. The total of 18% excess reactivity was selected as the optimum. More might cause difficulties with operation and shutdown, less, either no criticality or shortened life of the core. Operating measurements that have been made in the plant indicate that the reactivity calculations were substantially correct, and that the 5% design margin that was included can be used to provide additional lifetime for the core. The critical assembly also permitted an accurate determination of the control rod positions required to bring criticality. It was important that this be determined because in a power reactor, unlike an experimental reactor, the technique of adding fuel as a means of slowly approaching criticality is not practical. The preliminary experimental work done made it possible to predict the initial critical position of the control rods to within a fraction inch out of a total motion of 6 feet. The critical assembly also permitted measurements of neutron flux distribution. Since such measurements could be made only at room temperature, the ultimate check could be made only on the shipping port reactor under operating conditions. To permit such measurements, and thereby provide valuable information for use in the design of future reactors, an elaborate system of coolant flow and temperature instrumentation was provided at shipping port. Half of the seed and about 1/6 of the blanket fuel assemblies are instrumented for flow measurement. Approximately 2/3 of the seed and 1/4 of the blanket assemblies have thermocouples placed to measure the temperature of the water leaving the fuel assembly. Additional thermocouples at the bottom of the core give core inlet water temperatures. The temperature data and the flow data are used to compute power distribution in various regions of the core. Measurements which have been made indicate a good agreement with the physics calculations. To raise the power level, The control rods until the desired power is attained. Then they are moved back to the operating position. To lower the output, the opposite action is taken. No action is necessary to account for changes in electrical power demand imposed on this plant by the utility network. This is due to the large negative temperature coefficient of reactivity, which maintains a constant average water temperature in the primary circuit regardless of changes in steam demand. For example, if the inlet water temperature is 508 degrees Fahrenheit and the outlet temperature is 538 degrees, the average water temperature is 523 degrees. With increased steam demand caused by an increase in electrical output, the inlet water temperature may drop to 500 degrees. The reactor automatically increases power output, and the outlet temperature automatically increases to 546 degrees. Note that the average temperature remained constant, making the reactor plant virtually self-regulating. The value of this temperature coefficient was found to be -3 times 10 to the -4 per Fahrenheit degree at operating temperature, a value which agrees well with the calculations of this quantity. Nearly 2 years of design, development, and engineering were necessary before plans began to be definite and construction drawings made up. Then, in March of 1955, construction began with the clearing of the site. By mid-1956, considerable progress had been made. The force of construction workers numbered in the hundreds. By then, a large part of the concrete shielding had been poured. The container chambers were in place, and the canal section could be identified easily. With the reactor sphere in position, major equipment items began to arrive on the site. The 150-ton pressure vessel, having completed all of the shop processes involved in its fabrication, began its journey to shipping port. It was installed on October 10, 1956. The basic methods employed for installing the units were similar to those followed in major construction projects. A high order of cleanliness was necessary while the primary system was open, such as during installation of the thermal shield. The climax of these operations came on October 6, 1957, the precise placement of the fuel core in the reactor. The shipping port plant has a large number of newly developed items of equipment to ensure safety and reliability. Typical of these are zero-leakage canned motor pumps. In this design, no shaft seal is necessary. Metal cans enclose both stator and rotor. Primary water circulates between them, lubricating the bearings and cooling the induction motor. A separate water supply cools the stator coils. The turbine generator is outdoors, unusual at latitude 41 degrees north in the United States. The shaft speed of the unit is 1800 RPM. It is capable of producing 100,000 kilowatts in anticipation of future core developments. The shipping port plant was completed and full power operation was begun approximately 3 years after the start of construction, which is in line with the time taken to build non-nuclear plants. The total elapsed time from the award of the design contract was 4.5 years. Control of the operation of the plant is naturally divided into 3 parts: reactor, steam generation, and power generation. In addition, extensive instrumentation will provide a vast amount of information never before available. Among the continuous readings taken are water pressures, temperatures, flow rates, and power level in the reactor. In keeping with the developmental nature of the plant, a large part of the instrumentation is provided for indicating and recording design information and unusual events, and is not necessary for normal operation. Typical of this type of instrumentation is the extensive system designed to detect and locate fuel element failures. On December 2nd, 1957, the reactor went critical for the first time. This was the 15th anniversary of self-sustaining nuclear fission in the world's first reactor at Stagg Field in Chicago. On December 18th, 1957, with the generator synchronized with the Duquesne Light Company system, the first step was made to go to full power. On each successive day, the output was increased. At 50% output, the coefficient of reactivity was measured and found to be in agreement with preliminary calculations made at Bettis. The full output of 60,000 kilowatts was reached 5 days after synchronization. The city of Pittsburgh was lighted with the aid of atomic power at Shippingport. This new source of power had been put to work. It was a history-making accomplishment. Many operational tests have been conducted, and Shippingport has operated with an ease and responsiveness surpassing conventional power stations. In addition to its value as an operating power station, it is also to gain information to advance reactor technology. Tests are continuing for the purpose of carrying out this mission of the Shippingport project, to provide full-scale plant experience in development, design, construction, and operation. Experience that will be invaluable to the future of nuclear power the world over.